Today I'll be showing you the rotational inertia of a cylinder. And rotational inertia is just the sum of all the mr squared of the cylinder. So let's get to it. First, we'd want to split the cylinder into multiple rings or multiple hollow cylinders that have the same or multiple circles that have the same radius to the center point. In that case, the r's will remain the same for each circle. So yeah, we want to divide this cylinder into multiple parts with the same radius to the axis of rotation. After we have done that, we can find a general formula for the mass. So what does mass equal, or what does dm equal? We want to find what each individual mass of these hollow cylinders are. So dm would equal, well, let's first find the density of a cylinder. The density of the cylinder would be the total mass divided by the total volume, which is let me think, pi r squared h. All right. So dm would be the density times a small volume. All right. Now what's the small volume? Well, let's find it. So we want to find the volume of each individual hollow cylinder that we've split the cylinder up into. So this is a hollow cylinder. Let's name the length between the inner and outer circle dr. And okay, let me draw it better. All right. So this would be a cross section of this cylinder here. So this would be dr, and this would be the height of h, and the circumference. The circumference would be, let me think. It would be pi r squared, or no, it would be 2 pi r. Sorry, 2 pi r. So the volume of each of these individual hollow cylinders would be, well, 2 pi r times h times dr. All right, because we can just like divide the cylinder here and then unfold it until we get a rectangular prism like this. So we can unfold the cylinder into a rectangular prism, and the smaller dr gets, the more accurate our representation would be if we split it up into, or if we cut it open and make it into a rectangular prism. All right, so now that's the volume. So now that we have the volume, so volume times density equals mass, right? So now we can take our integral from, well, 0 to r. We have the volume here 2 pi r h times dr, and then we multiply, this is the volume, we multiply by the density, and then we multiply by r squared. And we're integrating this from 0 to r because each individual cylinder will have a, yeah, just from 0 to r. Yeah, it's hard to explain. All right, now that we have this integral here, we can take out the constants. So 2 pi h in rho we can take out. So 2 pi h rho. And then we just get 0r and r cubed dr, I think. Let me think. All right, yeah, that's correct. And if you know how to take an integral, this just ends up being 2 pi h rho times r4 over 4, 0r. And if we plug in 0, just the entire thing becomes 0. So we're just left off with 2 pi h 2 pi h density times big R4 over 4. And hence, now we can plug in what the density. So let's make this little h. So we get that this equals 2 pi m over pi r squared h times, well, okay, let's make this big H, whatever, times r4 over 4. Well, this cancels out, and this just simplifies down to, this becomes 1/2 big M r squared. And there you have it. That's the derivation of the rotational inertia of a cylinder if the axis of rotation is in the middle. Alright, so to repeat again, I split up this cylinder into multiple hollow cylinders, and then I want to take a sum of each of these hollow cylinders, right? And that would require an integral. And the only difference between each of these hollow cylinders would be the radius. So then I need to, find each volume of the cylinders, and then, yeah, it's kind of hard to explain, but all right, thank you.